Hey everyone, and welcome to a brand new explainer. Today, we're taking a wild ride from the invisible, quantum level of atomic bonds, straight up to the massive heavy-duty physical properties of the anvil. Think about it for a second. Every skyscraper, every car, every piece of industrial machinery out there relies completely on the hidden atomic secrets of the tools that shape them. Modern manufacturing just wouldn't exist without them. So we're unpacking the science behind high-performance tool steels, focusing on two absolute heavyweight elements that literally change the nature of metal: vanadium and molybdenum.
So here's the big question. How can mere fractions of vanadium and molybdenum so radically transform tool steel? It's honestly kind of like magic when you really look at it. You take a huge, heavy batch of molten iron and carbon, sprinkle in just a tiny fraction, literally a few percent, of these specific transition metals, and the alloy fundamentally changes. It goes from a metal that would easily deform under heavy industrial use to an absolute powerhouse that can cut through other solid steels while glowing red hot. No way, right? Well, the secret is hiding deep within the atomic structure.
To figure out how this works, here's our roadmap for today. We're covering 1. The atomic bonding foundation. 2. Vanadium versus molybdenum. 3. MC and M6 carbides. 4. Pinning the grain boundaries. And finally, 5. Optimizing heat treatment. All right, let's jump right into part 1, the atomic bonding foundation and the quantum mechanics of steel. To truly get a grip on these metals, we have to start down at the foundational atomic level. We need to look at how their electrons actually behave. It's super interesting because vanadium's contracted 3D orbitals behave entirely differently from the highly bonded 4D orbitals of molybdenum, and this single difference sets the stage for everything. Think of these orbitals as the electron clouds hanging out around the atom's core. As we move across the 3D transition elements, the increasing nuclear charge literally pulls those electron clouds tightly inward. They contract. Because of this, vanadium's smaller 3D clouds overlap pretty weakly with their neighbors. But then you have molybdenum. Molybdenum is sitting in the 4D series. Its electron clouds are well shielded, they're much larger, and they let molybdenum use all 6 of its valence electrons to form incredibly strong bonds without needing extra energy to get activated. It essentially sits at an absolute peak of cohesive bonding energy.
Moving on to part 2, let's scale this up. Vanadium versus molybdenum, and their microscopic properties.
Now, when you're engineering steel, the crucial point is that you are constantly balancing molybdenum's heat resistance against vanadium's extreme hardness and wear resistance. Remember how molybdenum forms those super strong bonds because of its large 4D electron overlap? Well, on a macro scale, that translates into high temperature creep resistance. That means the steel holds its rigid structural integrity even under punishing heat and stress. Vanadium behaves totally differently. Its main job in the steel matrix is refining the grain structure, which gives you exceptional hardness and resistance to surface deformation and abrasion. To put it in real-world terms, imagine vanadium as the razor-sharp edge of a high-end chef's knife that absolutely refuses to dull, right? While molybdenum is like the thermal tile on a space shuttle that refuses to melt under crazy atmospheric friction. If you want a tool that stays sharp, you lean on vanadium. If you need it to hold up under insane heat without warping, you lean on molybdenum.
Okay, Section 3. MC and M6C carbides, the microstructure battlefield.
Zooming out just a bit from those individual atoms, we land in the microscopic structure of the steel matrix. This is exactly where these elements get together and form distinct carbides. By forming these two entirely different types of carbides, we essentially achieve the holy grail of high-speed tool steel: crazy strength combined with thermal stability. You see, carbon is always looking for a dance partner in steel. When it pairs up with vanadium, it forms what we call MC carbides. These are vanadium-rich, incredibly stable, face-centered cubic structures. Basically, you've got atoms packed into tight, unyielding little cubes. They are small, they spread out uniformly, and they just refuse to dissolve easily, which is exactly what gives the steel its phenomenal wear resistance. On the flip side, molybdenum bonds to form M6C carbides. These are the ones locking in that thermal stability, making sure the alloy doesn't lose its temper, literally and figuratively, when industrial cutting generates massive amounts of heat.
And it is absolutely incredible to actually see this happen under a scanning electron microscope. This image proves the science right before our eyes, showing exactly where these M6C and VC compounds form during quenching at 1170 degrees Celsius. Check out the scan here. You can see the network of molybdenum-rich M6C compounds highlighted, while those distinct vanadium carbide grains are pointed out too. Having them dispersed throughout the matrix like this, that is exactly what metallurgists want to see. These tiny microscopic features act like literal shields, protecting the softer iron matrix around them from wearing away under intense pressure.
Which brings us perfectly to Section 4, pinning the grain boundaries and halting austenite coarsening.
Let's talk about a really cool phenomenon called grain boundary pinning. This is how vanadium physically forces the steel to maintain its fine structure under heat. Think of these fine vanadium particles as microscopic anchors. They physically lock the expanding austenite grains in place when the steel gets heated up, totally resisting structural degradation. Austenite is basically the high-temperature phase of steel where it gets moldable. In this one fascinating study, researchers took medium manganese martensitic steel and heated it to 820 degrees Celsius. At first, the austenite grains were an ultra-fine 3.98 micrometers. But here's the crazy part. Even after holding that intense heat for a full hour, 3,600 seconds, the grains only grew by 1.47 micrometers. This ridiculous resistance to coarsening happens because those tiny vanadium carbonide particles sit right on the borders of the grains, physically blocking them from expanding. The only way those grains can grow is if you push the heat so high that these vanadium anchors completely dissolve into the matrix.
As you can see by comparing these different conditions and magnifications, controlling the dissolution of these microscopic anchors comes down entirely to hitting the exact right temperatures. When the heat treatment is dialed in perfectly, we get this beautifully uniform distribution of vanadium grains, along with a tighter network of M6C molybdenum structures. But if that temperature gets too high, the anchors dissolve, the boundaries break free, the whole structure coarsens, and the steel loses all those precise mechanical properties we just worked so hard to build. Absolute thermal precision is quite literally everything here.
And that leads us to our final section, Part 5, Optimizing Heat Treatment and Engineering at the Forge.
This is where we step into the macroscopic, human scale, the forge. By following a meticulously calculated step-by-step heat treatment process, manufacturers guarantee the perfect distribution of both vanadium and molybdenum carbides in the final tool. Using specialized thermodynamic simulation software called JMAP Pro, engineers map out the exact recipe for this high-speed steel. Step 1, you carefully anneal it between 818 and 838 degrees Celsius to prep the structure. Step 2, you blast it with a quench right around 1190 to 1200 degrees Celsius. Just to put that into perspective for a second, that is physically hotter than flowing volcanic lava. This extreme quench locks those highly stable carbides in place without completely dissolving them. Finally, step 3, a tempering cycle between 550 and 600 degrees relieves the internal stresses while keeping that absolutely critical network of MC and M6C carbides intact.
So, what is the physical result of bridging all this quantum and microscopic science together? A tool with a staggering 63 to 70 Rockwell hardness. In everyday terms, that means it's hard enough to effortlessly cut through glass and slice right through standard steels. When you perfectly balance molybdenum's strong 4D orbital bonding for heat resistance with vanadium's ability to pin grain boundaries and form rock-solid MC carbides, you get metallurgical excellence. We're talking an 8 times increase in wear resistance over high chromium alternatives. That means factory rolls and industrial cutters can run for vastly longer periods without failing, saving massive amounts of time and money, all because we figured out how to manage atomic bonds. So, as we continue to master the quantum realm to forge macroscopic strength, it makes you wonder, what new limits are we going to break in alloy engineering? Thank you so much for joining me for this explainer. I'll leave you to ponder how unlocking even more atomic secrets is going to keep revolutionizing the tools that physically build our world. As our computational models get sharper and our microscopes peer even deeper, the line between quantum physics and heavy industry is just going to keep blurring. We just have to keep learning, keep analyzing the data, and keep pushing the absolute boundaries of what's possible. Until next time, stay curious.